Okay, so I think we can start. Uh, you may check your quiz, I think, later. Okay. Um, at the end of the course, maybe I will have maybe 5 to 10 minutes for you to check. Okay, now we're going to discuss about the indeterminate forms and the L'Hopital. Okay, so I think some of you know how to use L'Hopital in terms of limit. So what is L'Hopital? So I will explain first. Okay, what is L'Hopital? So if we have let's say limit as x approaching 0, let's say x approaching 0. Or maybe not 0, maybe just a. And if we evaluate and if this is 0 over 0, we call this indeterminate forms. Okay. So to understand what is indeterminate, we can just look at the word. Okay. Determinate means to describe or to determine something, right? Indeterminate means we are not sure what it will be. For example, okay, let's look here, 0 over 0. If we put a constant here, in terms of limit, any constant, any number divided by 0 will be infinity, right? It will be infinity. But if we put 0 here and this any number, it will be 0, right? So what this indeterminate form is actually is quite confusing whether it will be 0 or infinity. Which one is the first one? So that's why we call this indeterminate form. We cannot make sure what kind of evaluation will be. Okay, it is 0 or is it infinite? So we call this indeterminate form. When this happens, you may apply the L'Hopital rule. What is L'Hopital rule? I will describe first the method. Okay. I will describe first the method, and then we can see later what is actually L'Hopital rule and why it works, and what is at least the proof. Okay, what is the proof? So whenever you have a limit, let's say we have f and g. We put the limit. For f it's 0. For g also 0. Okay? Or for f it's infinity. For g also it will be infinity. So whenever this happens, and then we have f over g, and then we can have either both 0 over 0 or infinite over infinite. We call this indeterminate form. Okay? The way we take the L'Hopital rule is basically we take the first derivative on top, f front, and the first derivative on the bottom. Okay? And then what we are going to do next is we check the point, we check again. Okay? If it is still indeterminate forms, we can do more. We can do L'Hopital. If it's still, we can do more. Okay? Until when you put the a, you put maybe it will have some number, and we finish, and then stop. We got the result. Okay? That's how it works. Okay? Very simple, very easy. Okay? But the one that I want to firstly explain is basically what is L'Hopital rule and why it works. Okay? So I will show you later the definition again, but let me just explain first. Okay? So suppose that let's say we have a function, and the other function is let's say the ln. Okay. Okay, if we have this function, and we know that if we try to find the first derivative of both of this, we can do that very simple, right? We can just derive this, this become linear equation, this become 1 over x, right? This will be 1 over x, which we can also sketch the curve very easily. Now, if we sketch the whole curve, okay, we sketch the whole curve. Let's say we sketch, if you would like to say this, factorize this and make it x plus 4, right? And then x minus 1. So this will be the roots. So I think we can sketch this. Maybe that. Okay, maybe this is 1, 1, 2, 3. Let's say this is -4. This is 1. Okay, and then what is the minimum value? It's -3 over 2, right? So this will be 3 over 2 squared plus 3. Just very quickly, just to estimate what is the minimum value. 9 over 4, negative 9 over 2, so negative 18. Negative 18 plus 9 is what? 9 over 4. 9 over 4, it should be 16 over 4 minus 9. So it should be around, maybe around here. Maybe this will be 1 over 5, 3 over 2 is here. Let's say around there, okay? Well, not there, sorry, this one. Should be this one. Let's say this is the minimum value. Actually, the minimum value is not important now. Okay. And then we have ln x, right? We have ln x, which is supposed that to cross this. So let's draw. Let me correct this first to make it clear. Okay, maybe like that. And then we have ln x, which is going to be maybe not quite. Maybe like that. Okay. Okay. I think I need to check whether it's correct or no. X squared plus 3x minus 4. Okay. And then this should be ln x. Yeah, I think quite okay. We are focusing on the here is, but this one should be here. I think still. We focus on this one, okay? Focus on the x equal 1. Okay, when x equal 1, f1 becomes 0 and g1 also 0, right? So at this point here, okay, so that's this point, all, oh, why is gone? Okay, that's all the point when the function becomes 0, right? Okay, now if we try to approach the limit as x approaching 1 of this f of x over g of x. Okay, so this one is the f. Okay, this one is g. Okay. Now if we try to zoom in this part here and we know the linear approximation, okay? basically linear approximation says that we can approach the functions with the tangent line, with this tangent line, right? So if we look at the tangent line here, so let me draw the tangent line. And then the other one. So perhaps in this point, they are actually very similar to the counterpart, right? So we can see that. Let me make this a little bit bigger, maybe here. Okay, and then this one. Okay, and then let's say this is. Let's say this is dg, okay, and then this is dx. And then this is another one. This is df. And this is another dx. Now, if we supposedly that if we are just observe on this small area, we could see that if we are trying to define f with g, the ratio on that small area is the same with the ratio of the tangent. Okay? Now if we break to the tangent becomes 2, I hope you can clearly see this. It's actually two triangles, the red and the yellow one. Okay? The yellow one is for the tangent of the g, and the red one is tangent of the f. Okay? So basically we are saying that when we take this, f over g, is actually the ratio between the tangent. So this is actually the df dx over dg dx, which literally our definition of the first derivative. Okay? Okay, of course, this is by intuition and by looking at the graph, by visualization. Okay? So actually, why the L'Hopital works is because we are observing this area, and by implementing the linear approximation, we know that when we approach the nearby area of this, when the function is equaling to 0, so if we have two functions, and then both of this ratio will be true, and this will be equaling to definition of the derivative itself. Okay? It's not quite yet like proving with the equation, but we try to sketch and see that it's actually similar. So we can say that, okay, it seems that our approach is, I think, it might be true, right? Okay. So I hope you get the idea from here. Okay? So that's why in L'Hopital, you derive the top equation, you derive the bottom equation. Okay? It means that you are approaching the tangent line. Okay? You're approaching the tangent line. You're approaching function with the tangent line. Okay? I think maybe to make it a little bit clearer, I think you can see this picture here, okay? Just to make sure that we are on the same page. So we have f and g. F and g can be any functions. And then if we try to make a tangent line from f and g, at the same point here, let's say when the function is equal 0, here, we can see that actually at this nearby point, the A, they are quite similar. Okay? They have the same behavior. Approximation is quite similar, right? They are quite getting closer to the real value. So we can say that from here, that the ratio between the two functions
like the m1 over m2. Let's say this is m1 and m2 is the ratio for, so let's say this is having the slope, both of slope. This will be, so every time we have this, so it suggests that we can have our first derivative. Okay. Okay.
Now after this, I will show you how to set up the proof. Actually, not really a proof, but intuitively maybe it is a proof. Okay.
Okay. Okay, now we are going to see, our goal is to make that we have this L'Hopital, right? This is the, so our goal is we want to make this happen. So what can we do is actually we start from here. Okay, let me make a little bit. Okay, so we start from since f of a, so since f of a equals 0 and g of a, or maybe let me write f of a is equal g of a equals 0, it means that
if we add something here related to f of a or g of a, it's 0, right? Because it's 0, we can, let's say, minus f of a minus g of a, because we actually subtracting with 0, which is not really change anything, right? So let's say we take the minus of f of a minus of g of a without changing anything, right? And then both top and bottom equation I will multiply. Okay, so this multiply with, so I can multiply with something like a over a, right? Because a over a is just 1, so it's okay, right? So let me just multiply this with 1 over, maybe let me make it, so this is 1 over x minus a, the bottom side also 1 over x minus a. Okay, now suddenly we see that we have this definition, f of x minus f of a over x minus a maybe let me write this a little bit down here. Okay, which this is actually, this is limit definition. Okay, limit definition for derivative. Remember, we have two forms for the limit definitions. The first form is this one. Okay. Really important. Okay, really important. Both are the same meaning, okay? Just different approach, but the same conclusion.
So if you are asking what is derivative, you can either using this fx plus h minus f of x divided by h, or f of x minus f of a divided by x minus a. And the limit is h approaching 0 for the first one, and x approaching a, okay, from the chapter limit. Okay. Now we have this. Okay. So we have the second definition, right? So actually, this is the f prime a, right? This is f prime a. So this is f prime x. This is f prime x. Okay. So we have now limit f prime x and then g prime x. And what you need to do is you need to plug in the value x equal a, and suppose that this is the complete answer, then this will be having some value. Okay. If it is still indeterminate forms, you can do another L'Hopital rule. Usually, when you write the L'Hopital, usually you need to add. So let's say this is the question. So you need to add the symbols LH here. Okay. Just to confirm that you are doing L'Hopital on this part. So this is the question, and you are doing L'Hopital, and this is the result, and you plug in the value, and that's it. Okay, that's it. Okay, sometimes in limit, L'Hopital may make the calculation faster, probably. But not always. Not always. Sometimes maybe you need to do some arrangement and then L'Hopital, or you can directly L'Hopital and then do some arrangement. So you can have some ways. So it doesn't mean that this is like a final solution. You need to do all L'Hopital. Okay? It doesn't always work like that. But it is like one option that you can do. One option. Okay. So midterm will include limits, including L'Hopital, all the derivative techniques, including the related rates, including the approximation, and also including the sketching curve. Okay? At least sketching curve. So yeah, sketching curve. Okay. So you need to draw a graph. So my suggestion is bring ruler. Okay, bring the ruler. Bring the ruler. Okay, limit, derivatives, all the techniques, related rate, linear approximation, and the sketching curve. Okay, sketching curve. Sketching curve include the first derivative test, the second derivative test. Okay, including all in the sketching curve. The asymptotes, blah blah blah. Okay, there's a lot of this sketching curve. So include all. Okay, it will be different vibes from the quiz. I believe quiz is happy event. So this is a little bit scary. Okay. Some quick example how we are using it. Let me just give you like a really simple question on limit. Okay. So suppose that we have, so this is example. So let's say we have limit x approaching infinity. This will be ln x, and then square root of x. So when you know this, sometimes when you know this, we have the ln in the limit, and you check. First, you need to check. Okay, you need to check input. If it is indeterminate forms,
you can use L'Hopital directly. Sometimes there is some question that when you input, it has some value, then you cannot L'Hopital, okay? Sometimes you are too exciting and then you L'Hopital everything, and then that's wrong.
Okay, so check first, okay? So please check, okay, please check first. So I think it's okay to do L'Hopital for this one. So we take the LH, okay? Since this is infinite over infinite, right? I just mark the symbols. It doesn't mean that you need to write like that in the exam. Okay, and then we write the derivative of each equations. Okay? So ln become 1 over x. The square root of x become 1 over 2 square root of x. Okay, sometimes
we are probably maybe we have this and then oh, we put here, oh, 0 0 L'Hopital again. You need to arrange first, okay? You need to rearrange first because this is not yet complete in algebra form. We need to fix the structure first, okay? Because x and square root of x we can at least cancel, and then the other one have the square root, right?
So we can have, this is limit so we can cancel this with, and then we have the square root of x there, which this is going to be limit, and we have 0. Okay.
So don't forget to rearrange every time you have some structures like this. Rearrange first. Sometimes this is intimidating to, oh, we see that the 0 0 indeterminate forms. But rather just slowly rearrange the structure every time you take the L'Hopital. Okay?
Okay, maybe let me arrange this, move a little bit down here. I will need to write something. Okay, another example, limit x to 0, tangent x. Okay. Oh, sorry. It should be cube. Okay. Okay.
And then remember, check first. 0 0 0, so 0 0. So you can use it. Can you try this one? Can you try this one? Try to solve. I would like to know, like, if the question having some trigonometry, limit, and the L'Hopital.
I think I will copy this. Okay, I think maybe you need more space, so I will copy to the next page. Okay.
Yes. Oh, you want to take?
here. Okay. Oh, which one? The whole or which part? The whole thing? Is it too small or okay? It's okay?
If you need like which part, the top one or the bottom one? The top one.
Okay. Maybe here, right?
Okay.
Can anyone find the answer?
This one? Okay. You have to see it. Yeah, this one. What should you do?
I don't know, maybe I got very lucky again, so this is turn.
Okay.
But I don't know.
There are another way. Yes. Yeah, you need to speak some identity limit using this. You can get the answer directly. But it is okay. Yes. I mean, how will you get yes. What is the
No.
every variable, right? It means that this should be then you then become second square minus one.
Sí, cuando quiero cuadrado porque yes, like this. Oh, deep. No. Yes. I couldn't follow it.
No, I think you need to get more study on algebra. After getting yeah.
Try first, okay? Okay, first check, right? Check this. It's 0, 0, so we can take L'Hopital. Okay. So we write derivative of tangent x. It's secant squared x minus 1. This is 3x squared, right? If we put 0 inside, check again.
The secant squared x is 1, right? So it's 1 minus 1 is 0. 0 down here is 0. So another 0, 0. So there are some options. You can do another L'Hopital, or maybe you can do some arrangement here. What I mean by arrangement is usually we have a trigonometry. So can you relate some identity with this secant squared?
Yes, that one. Okay. So, and if you forget how to relate secant squared with other trigonometric identity, you can start with the basic one. Okay, start from here. Let me explain very quickly. You can start from the sine squared x plus cosine squared x. This is equal 1, right? Okay, divide all with cosine squared x. Okay. This will be tangent squared x. This will be 1. Okay, and this will be 1 over cosine squared x, which is secant, right? So this will be okay. So actually we can rewrite our secant squared, the one that we have in the question, become tangent squared plus 1. Okay? So the first options, okay, I will use this way. Okay, so this will be limit. So this will be tangent squared x plus 1 minus 1. So we have cancelled this one, right? And then the bottom here is 3x squared.
If you are trying to take 0, it's 0, 0 again. But we have some identity actually in limit. If you remember that if we have limit sine x over x, this is equal 1. Okay. This will be also equal for the tangent. This is also equal 1. Okay. Okay. So I will factorize the 1 over 3, and this will be actually okay. There are some proving how to from here to here. Okay, this one is from geometric perspective. We find that is using squeeze theorem, if you remember, and then we completed. Okay, it's equal 1. Okay, and the other form is using the cosine. Okay, I also don't really remember, but yeah, we cosine.
So since this is 1, this is 1, then this will be 1 over 3. Okay. Okay. So a little bit review on limit, especially for the trigonometric.
Another way is you can one more L'Hopital, you get something here, and still need this, okay, to make it equal 1.
So let's say we have another L'Hopital, since it is still 0 over 0. So we take this is 2 secant squared x, tangent x, and then 6x. Okay.
If you are maybe thinking, if we put 0, it's still 0 over 0, try again. I think we can have something, but I don't suggest like to derive every time. Every time you have a trigonometric, you can think some identity. Okay? Some identity.
So this will be 2, this become 3, right? So we can also write. So this is the first way, okay, this is the second way. Okay. So this will be limit. Or maybe let me write 1 over 3 outside the limit. This is secant squared x, and then I will separate the secant squared and then the tangent. So this is limit. So this is equal 1. Secant also equal 1, right? It's like a cosine. So you get 1 over 3. Or you could use the sine x over cosine cube, which I don't recommend you to derive.
You can derive again, but I'm not recommending it.
Okay, any question first?
Any questions? Okay. So, any trigonometry, you need to be aware of the trigonometry. Okay.
Okay.
And indeterminate form is not only 0 over 0 or infinite over infinite. We have some others as well. And we'll finish that all the
Forms, hopefully by today or maybe this week. Okay. But I think today we can finish, at least just to give you the descriptions. And then after that, maybe some example. Okay, the first one we call let me write the name, indeterminate products. Okay, for example, let me just start with just giving you x ln x. Okay.
So we have this x ln x, in which if we try to look at the value, with the x value that we want to approach, this is approaching 0 from the right. Since we have the ln x that is going like that, so we can imagine that it's going to approach from the right. X is 0, ln 0 is infinity. So it is, again, we kind of confuse whether it's going to be 0 or infinity. So we call this indeterminate products. Or this is 0 multiply infinity forms. Okay. For example, in another case, let me explain again later for the example. Let's look here. Okay, we can have a break first. Let's continue for a while.
I'm going to see for you.
Okay, now we can consider first, okay, before we start to how to solve in general, to solve the indeterminate products in general. So consider we have this limit, okay, and then we also have, so this is another one. So we have another one, which we have limit x, this is equal to 0, right? And then we also have limit 1 over, now it's x squared. And this is still infinity, right? And then if we multiply this two, this becomes infinite. Okay, so there are two possibilities. So we have x squared, and then we have 1 over x. Both are 0 and infinity. But if we multiply these two functions, x squared and 1 over x, we have x, right? Which it turns out to be 0. But in another path, we have x and 1 over x squared. So we switch the functions. Okay, so switch the functions x and x squared, 1 over x squared. If we multiply, it will be x multiplied with 1 over x squared, which is resulting 1 over x, which we find the infinity. So we kind of having 0 and infinity. Okay, so which one is the answer? Right? In another way, if we have, for example, if we have another possibility, let's say we start from x equals 0 like that, and then we compare with 1 over x, which is another infinity. If we multiply these two and take the limit, we have x multiplied with 1 over x. We have 1, right? So which one is the answer? So it can be 0, it can be infinity, it can be 1, right? So the idea here, okay, the idea here is we are going to, so this is several examples, okay, so several examples. So example for indeterminate products. Okay, so it can be 0, it can be infinity, it can be 1. Okay. So whenever we have, let's say f, and then multiply with g, notice that we can cancel this, right? We can cancel. So if we could somehow make f or g reciprocal, it means 1 over that function. For example, we can make the f g, and we can rewrite this as f over 1 over g, or maybe this is still true, right? And then we can also have another way, it's g over 1 over f. So both of this, if we check each one of them, if it is 0 over 0 and it is indeterminate forms, then we may apply the L'Hopital rule the same as the previous one. Okay. So, for instance, if we can rewrite the limit for x ln x, if we can rewrite this as
we can have infinite over infinite. If we write like this, which we can apply our L'Hopital rule. Okay.
so that's the whole idea. So this will be 1 over x, and the bottom side is negative 1 over x squared, in which we have limit of negative x, or if we plug in 0, this is just 0.
You can choose the other one, like x over 1 over ln x, but perhaps it's going to be more complicated. So if you have like a random functions and perhaps it is similar to this one, indeterminate products, you have two options. You can try this one, the f over 1 over g, or maybe g1 over 1 over f. You can choose the one that maybe looks more simple.
And by the way, there will be no TA class today. Your TA, I think, gets sick. So she will give you some assignment and maybe additional content. Okay? Do you have class after that? After TA? Do you have class? Oh, okay. If no class, then you can go home. I know the feeling, okay? I was student too, so I would go home.
The one on the right side is some combinations that how the results might be. The left one here is some of the methods that we may apply, and also it will depend on what kind of function that shows here.
Okay, another forms, still indeterminate. We have at least 4 forms. So this is the first one. The original one is the 0 over 0 or infinite over infinite. The second one is 0 infinity. And then the second one is the indeterminate difference. Okay, differences mean there will be some subtractions. Okay, so we have, so suppose we have limit of the f of x, which is infinity, and we have another limit, let's say another function g, also infinity. Now this is if we have f of x minus g of x. Now this is what we call the indeterminate differences. Okay? So it will be the type with, so it is, the type is infinite minus infinite. Sometimes if you are really not paying attention to the problem or the question, sometimes in the exam you find this, and then you see this, and then you see
0. So maybe you get drunk.
So this is not equal with, so never write this, okay? So let me wait there, okay?
Okay. Anyone can explain why? Why it's not equal to 0? Yeah. Why?
It's like the water in the bottle is infinity. Water in lake is also infinity. So if you minus infinity, you don't know water.
Okay, good idea. Or you can say that since infinity, if you think in accountable numbers, you will not get anything, right? You will not reach any number, right? So this actually not a number. Infinity is abstract. It's a concept. So that's why it's not happening. So we are not sure whether it will be in this infinity or maybe negative infinity. Right? It will be the right or the left, which one is bigger, right? So it doesn't work like that. Okay? So never do this. Okay?
What? Okay. Okay, so I think we can have some example, and I will show you how. Okay, and this is quite direct. So let me just take example. So I take limit. Okay, we see that if we have this is the infinite minus infinite, right? Okay. So the way we do it is basically if we have a
Fractions like this, then perhaps we arrange first. We arrange all of this, make it into
combine these two, it become one fraction. So let's just combine, and then maybe right limit. And then this will be ln x minus 1. Okay. This will be x minus 1. And this will be minus ln x, right? Okay. So what will happen?
what will happen if we check with our limit here. This will be 0, 0. This will be whole thing will be 0. So 0 over 0. So the idea is actually we are trying to force out the structure 0 over 0. So most of the indeterminate forms, the method is we need to change the structure into 0 over 0 and then use L'Hopital. Okay.
So mostly it will work. Okay, mostly it will work. So from this, we can check that this is 0 over 0. Okay, and then we can do L'Hopital. So x become 1, negative 1 becomes 0, and ln x become 1 over x. So minus 1 over x. Okay. And how about this one? We need some product rule. So 1 over x, x minus 1, and then what? Plus ln x, right? I think I will remove the x, so I will let me multiply with x over x. So limit x, so we have x minus 1 over, this is x minus 1 plus x ln x. Okay, check again. I think we checked 1 minus 1 is 0, 0, 0. So 0 over 0. Maybe one more time, take L'Hopital. Maybe let me write this here. And take in there. And then L'Hopital. So this will be 1, 1. And then plus ln x plus 1, right? And then we check again, this will be 1 over 2. And sometimes we just need some definition and some understanding of the curve to answer. No need to like write something. For example, let me just write the question first. Okay. Like this type of question, e to the power of x and then negative x. This type of question is question, like sometimes you don't really need to calculate with some mathematics notes or forms. We just need to understand how the curves will work. We have x, which is linear, and we have exponential. Which one is faster? Exponent or linear? Which one is faster? Increase faster. Which one? Yeah, exponent, right? So by doing that, we know that this will be going to infinity. Okay, you get my point? Or if we take, maybe if we write this and taking x outside, this e to the x over x, right, minus 1. Okay. We are going to see that the e to the x over x, this will going to be infinity as x is going to be infinity. Or we can write that e to the x is largely faster than x. I mean, this one is, you can try verify using L'Hopital. So take L'Hopital, because it's infinite over infinite. So we have e to the x and then 1, and this is infinity, right? Which means that the whole part here is going to be infinity when we enlarge the x. And when we increase the x, this will be getting larger and larger. So the e to the x is increasingly faster than the x, which means that this whole thing will be equal to infinity. So, or we can write directly by understanding the curve, this will be infinity. Okay, any questions? Any questions? Okay, so basically the idea is to make it 0 over 0 or infinite over infinite situation. Okay, now the next form, next form is we have power. So we might have limit power like that, and we have several conditions. if we have f and g becomes 0, so this is the 0 with power 0. This is okay, we have 3 conditions. Okay, so we have conditions. So this is the conditions. So condition. We have 3.
Okay. So the first one is 0 with power 0. Okay. The second one is infinity with power 0. And the last one is quite unique. It's 1 with power infinity. Interesting, right?
Okay, to start with, okay, if we have, let me write 1 with power of 20,000. What is equal? 1, okay?
But here, in terms of infinity here, it's different from this part. It's a little bit different.
I think if we have time, I can explain. But let me give you some example first, how to make it true, okay? And then, oh yeah, I think if we have time, okay? So let me give you example first, and then we can have some conclusions. So only one form that is not
Here, which is the 0 with power of infinity. It's not here. Then it will be 0. I think maybe next Thursday I will talk about that. Okay. So let me explain first how to deal with this. Okay.
So, example, if we take limit there are at least 2 ways
To work with this. Okay. Remember in differentiation, like last time, when we have function with power of functions, the best way is to make this x going down. Right? Either we can use ln, or we express this with e. E with power of ln this. Right? So
let me write just 2 separate ways. Okay. So let's say we have the first one is we take the limit of x with power of x like that, and then we change and write e with power of ln x power of x. Okay. And then from here we can write e x ln x.
since e is a constant, a Potter constant, then the one that we approach is actually the power, right? Only this one. So actually we can move this to here, so we can just focus on finding the x ln x. And since x ln x we have done before, right? The first example, which is 1, right?
So which is 0, sorry, 0. So we can write e with power of limit x ln x. Or in this case, we have e with power of 0, which is 1. Okay. Another method is we let y equal x with power of x. Okay. And then similar with what we have in the previous chapter, we take ln both sides. So take ln here, take ln there. So we become ln y is x ln x. And then we take the limit. So take the limit and take the limit. Okay. We know that the limit on x ln x is going to be 0. So since this is 0, then the ln y is also 0. So limit x ln y is equal 0. Since this is 0, then y is e with power of 0, which is 1. Or we can write just like on the left, we can write limit I think this is the same thing. I don't think we need to write this, okay? Maybe, yeah, I think this is all okay, I think. So,
notice that if we take the limit for the ln, okay, sometimes this is, I think, frequent mistake for students. So you try this, and then you find 0, and then you forget to bring back to the e. So don't forget that this expression for the limit is for the ln. So we need to find the limit for the y. Okay? Or you could try the left one, directly the left one. So basically, you are getting the final form, which is e with power of this, which is e with power of 0, which is 1. If you try this, the one that you get here is in the power. So you need to bring back to the e. Okay?
so that's the example. Okay, similarly, if we have another example, limit as x approaching infinity, this is x, this is 1 over x. Okay. This is so the first one here is the 0 with power of 0. This is infinity with power of 0. And you can use the similar way to work this out.
Okay? So you can directly write in terms of e, and then you are going to limit the power, or you can try to take the ln, take the limit, and then bring back the result into the power of e. Okay?
Okay, so
Many faces look stunning. Either you get it or maybe you are getting confused. Okay. So basically, in terms of power, I think the idea is very similar to the previous derivative. The idea is this power makes things difficult, right? So we need to remove and make it down here. So to make it that way is we need log, right? We can take log like this, or we can exchange into exponent. Okay, hope that's clear.
So for this one, the second one, if we let this become is y equal x with power of 1 over x. And then we take both sides ln, like that. We can have 1 over x and then ln x. Okay. And if we take the limit, then we have the infinite over infinite, right? Which we can take the L'Hopital rule. So take L'Hopital. So this will be 1 over x over 1. So 1 over x, which is equal to 0. So this is the ln, right? This is the ln. So the whole thing, so y is equal e with power of 0, or this is the limit or maybe let me write this is limit or you can directly write from here. You can directly write e ln and then x with power of negative 1 over x. And then you take the L'Hopital. This is 1 over x, or this is e power of 0 is 1. So the same result, okay, the same conclusion. Okay, for the other example, for 1 with power of infinity, example is like this, x, let's say 1 plus ln 4 over x. Okay. So it was obviously, if you put infinity here, this will be 0, this is 1, right? But 1 with power of infinity. So this is for 1 with power of infinity. So I think we can start taking let y is this, okay? And exactly the same method. So basically, I think most of the powers take the ln. Okay, take the ln. So take the ln both sides. So we have x ln 1 plus and 4 over x. So it's like a huge fractions. But when you do this, we have another indeterminate form, which is if we take the limit. So let's take the limit. So if we take the limit for this one, this is infinity, this is 0, and 1 is 0. So this is infinity 0, right? It's not good, right? It's not good. So to work out this, we need to remember
how to force out 0 over 0 or infinite over infinite from here. Okay. So the best way, I think, you see, you can have two choices. Okay. Let's say this is x is f, the ln whole thing here is g. We have two components and two functions f, g. Okay. So let me write here.
So let's say this is f, g. Okay.
Remember, we can make the x become 1 over x down here, or we can make ln 1 over ln down here. I think you agree that 1 over x will be much simpler, right? It will be easier. So let's try to do that. And if you look the evaluation, if we put infinity here, this will be, the whole thing will be 0. Okay? So this will be a 0, this is ln 1, so this is 0. And if 1 over x here, this will be 0, so 0 over 0. So I think that will be for the best for our
Solutions. Okay. So I think this is equal to, we can write ln 1 plus and then divide by 1 over x. Okay. And now we can take the L'Hopital. I think I will move this going over here. Okay. So we take with L'Hopital. For the denominator, this will be negative 1 over x squared. And for the ln, what will happen? It's a little bit messy. So let me write here 1 over ln 1 plus. And then this one is negative ln 4. Right? Chain rule. I'm going to multiply this with this. I'm going to bring to the top. So this will be cancelled, this will be cancelled, right? So we have, oh, why we have ln here? Okay, it's ln become 1 over. Okay. Correct, right? Or no? Yeah, I think okay. Okay, and then we can start to write limit ln 4 divided by 1 plus ln 4 and then we can check again, check here, this will be 0, so it's 1, so this whole thing is ln 4. But always remember that this is, the ln 4 is the ln y. We need to change back to the y. So we need to get ln 4 into the power of e. Okay? So since limit ln y is ln 4, then y is e with power of ln 4, or this is 4. So this will be 4. Or if you prefer to change this into, let me write with green, e, and then we have ln, or let me write limit. You can also start from the e with that power.
And then basically the same thing. You need to approach this and forcing the 0 over 0 or infinite over infinite situation. So most of the problem in the indeterminate form, you can solve it by forcing the structure becomes 0 over 0 or infinite over infinite. So generally in the context of the L'Hopital rule, finish. Okay, so we have more practices maybe after this. Okay? Perhaps maybe practice for midterm preparation, right? Okay.
Okay, any questions? Any questions? No? Let me write some notes for the next Thursday. I will explain more. Okay. And then we can finish. Okay. Okay. Let me write some notes. Suppose f is positive function if limit so this is for the 0 with power infinity. I think I don't have time to finish this one. This will be on Thursday. Okay, I will continue on Thursday.